As you probably know, students in various majors are required to take Math 243, the statistics class you're in. And, some students, as you might expect, enjoy the class and feel that it's useful, perhaps, to them. And other students may not feel that it's so useful at all. So the question we're going to investigate here is whether students in different majors feel differently about how useful this class might be. So one way to do that would be to gather some data. And so we're going to suppose some data was gathered. Some students in Math 243 of different majors were asked whether they thought the class would be useful for their major. And the results we get are displayed by this two-way table. So you can see what we have is we have two categorical variables. Over here is the major, and over here is whether or not they felt like the class would be useful in their major. And so we have two variables, the usefulness and the major. And so you can see there's numbers in here. This number 18 indicates that 18 of the students questioned are majoring in psychology and feel like the class will be useful in their major. Over here we have 14 students majoring in something other than dental hygiene, psychology, or communications who feel that the class will not be useful in their major. And so if we look across here, we can see that perhaps the communication and psychology majors feel fairly strongly that the class will be useful in their major, and the dental hygiene and others don't feel the same way. But what we really want to know is whether these feelings would hold in general for all students that would take this course. And so because we're thinking about all students but basing our results on just these students here, we're doing inferential statistics, and in particular we're doing a hypothesis test. As you can guess from what we have up here and from the table, our null hypothesis would be that students of different majors all feel the same or about how useful this course would be. And our alternative would be that students of different majors feel differently about the usefulness of the course. And so those are the hypotheses that we want to test. So there's some language we need to know in order to do the appropriate test, which is a chi-square test. We've talked about that before. And the language here is, first of all, that this table has what we call cells. These 8 spots here are called cells. These 4 cells are the first row of the table, and then this is the second row. So this table has rows. It has columns. And these numbers that are in here are what we call observed counts. They're counts of how many students are in each category. And the word observed indicates that they're what we saw, or they're what we observed based on our real data from students. Now, to conduct a chi-square test, the first thing that we need to do is add some numbers to this table. So the first numbers we'll add what are called rows or column sums. We add each column down the column. We get a 16 here. 18 and 5 is 23. 5 and 1 is 6, and 12 and 14 is 26. So these down here are called column sums because we've added up each column to get those numbers. And over here we have corresponding row sums. We have 44 in this row and 27 in this row. And so these numbers out here are counts, and they're what we call marginal counts. This represents the total number of dental hygiene students, the number of psychology, the number of communication, and the number of other. And then, of course, the 44 represents the number of students that felt the course would be useful in their major, and the 27 is the number that felt it would not be useful. Since the students in the 4 different majors comprise all the students, if we add those up, we should get the total number of students, which was 71. And of course, we should get 71 if we add this way as well, and we do. So these numbers out here, as I may have just said, are called marginal counts. These are row sums, column sums. And this thing here is called the grand total. So Let me write that in, and over here these are row sums, and down here we have column sums. Now, the next thing that we need to do is compute something that we call the expected counts. These were the observed counts, and now we need expected counts. And what the expected counts are they are numbers that would be in each of these cells that would maintain the same marginal counts, but would give the same proportion for all majors. In other words, they're what we would see in here if the null hypothesis was true. That is, if there were no difference between the different majors. Now, when we get these, they aren't going to be whole numbers like the observed counts. They will be decimal numbers. And so what we need to do, here's our table for that, and we need to fill in the cells of this table down here based on the numbers that we have up here. And the process for doing that is relatively simple. I go to a cell here, and the way I get what goes in there is I go up above to the corresponding cell here, and what I do is I look at its row sum, 44, and its column sum, 16, and I multiply those two numbers together. So we take 44 times 16, and then, so those again are the row sum for the row that this cell is in, and the column sum. We multiply those together, and we divide by the grand total. Okay, so again, it's row sum times column sum divided by the grand total, and when we do that, the result we get in here is 9.92. So let's do another one to see how that happens again. So let's say we went to this one, this cell. We take its corresponding cell up here, and we look for its row sum, 28, and its column sum, 27 and 6, and we multiply those, 27 times 6. Again, we divide by the grand total. We always divide by the grand total. So it's 27 times 6 divided by 71, and that gives us 2.28. Okay, so that's how we get the expected cell counts. So down here, these are the expected, and up here, these guys are the observed counts. So what you should do is, why don't you pause the video right now, and while it's paused, figure out what the expected counts are in the remaining cells, and then when you hit play again, we'll fill those all in together to see how you did. So go ahead and hit pause now and compute those expected cell counts. Okay, so we're back and we're ready to fill in these counts, hopefully with values that you obtained. So the expected count here is 6.08. Up here we have 14.25. Here is 8.75. Up here is 3.72. In this cell we have 16.11. And here we have 9.89. Let's say that we'll use the convention that we'll always round these to 2 places past the decimal. When we do our next computation, we're going to want to go to 3 places past the decimal, but we'll do our expected cell counts to 2 places past and leave that at that. So what we're going to do here is end this video and actually pick up the process again on the next video. So let's recap what we've done so far, the steps. We started out, we have our two-way table for our data that has the observed cell counts. The first thing we do is compute our row sums, column sums, and the grand total. Then we need to fill out this table of expected counts, and each expected count is obtained by multiplying. We go to the corresponding cell up here, multiply the row sum and column sum for that cell together and divide by the grand total. So again, for this cell, we took 44 times 16 and divided by 71, the grand total, to get this value. That's how the expected cell counts are found. And we'll see in the next video what comes next.